Okay, so what are the similarities here? Well, if you look closely, you'll see that all the determinants are identical, right? And the coefficients, they all differ by exactly a sign. So really, as a consequence, these two expressions they differ only by sign. So let's put it this way. Yeah, let's say it exactly like that. These expressions differ by a negative sign. And by that I mean the determinant of A with the cofactor expansion we got up here, and the determinant of B, the cofactor expansion we have down here. Okay, so is that going to hold in general? And the answer is yes. So it's not just for a general 3x3 matrix that's going to hold, and it's not just the first and second row being interchanged that makes that happen. If you have any square matrix and you interchange two of the rows, it turns out you're going to change the determinant by a negative sign, always. So if the determinant was negative, you're going to make it positive. And if the determinant was positive, you're going to make it negative. So how can we write that as a rule? Let's say it like this. If A can be carried to B through the following row operation, in other words, by interchanging two rows, say row I and row J. That's how I'll write this. So if A can be carried to B by doing that row operation, then the way that the determinant of A and B are going to relate is just that determinant of B is negative the determinant of A. So I know I've already said it, but let me just say it out loud one last time. So if you interchange two rows of a determinant, you're going to change if you interchange two rows of a square matrix, you're going to change the determinant by a factor of -1. Really, you're just going to change the sign of it. Okay, what are some other things you can do with matrices? What are the other elementary row operations? Well, the next one that we're going to look at is if you multiply a row by a non-zero constant. So you can see I've actually chosen to refresh the definition of the matrix B. So the idea is now instead, remember what we did on the previous page, A was written down as a general 3x3 matrix, and we let the matrix B be exactly what you would get from A if you interchange the first and second row, and that's what we got here. So forget about this now. We're going to reset this, leave this A as it is, and now we're going to instead now let B be this matrix, which actually, if you look closely, you'll see that those are exactly the entries of the matrix A, the original matrix A on your previous page. Pause this video and take a close look, again, to make sure I'm not pulling a fast one here. But the matrix B is exactly like this, except the second row has been multiplied by 4. That's the only difference. So I've actually already worked out the cofactor expansion here to show you what happens. So if you were to do cofactor expansion of the matrix B along the second row, well, what would you get? You'd have the determinant of B is equal to the following. Here we've got, do cofactor expansion. So negative, positive, negative, that's where the negative, positive, and negatives come from, because that's the locations, that's the sign that those entries correspond to, or their locations correspond to. But if you do cofactor expansion along the second row, you're going to get negative 4A21 times the determinant of the top two entries and the bottom two entries over here, and that's what's right here. Then you have plus 4A2 times the determinant of these 4 entries on the outside. That's where this comes from. And then lastly, minus 4A23, that's right here. And then the determinant of those top 2 entries and those bottom 2 entries there. And that's where this determinant comes from. Okay, and well, what do you get here? Well, what happened? All of those terms have a common factor of 4, right? There's a 4 here, there's a 4 here, and a 4 here. So what happened? Well, factored out of 4, and you end up with this. 4 times this expression down here. Now, what is this expression down here? It turns out that it's exactly what you would get if you were to perform cofactor expansion on this matrix A using the second row. And I encourage you, that's not something that you're just going to look at for 2 seconds and it'll be obvious. You actually have to check. So as an exercise, I would say pause this video for a moment and just write out the determinant of this matrix A, doing cofactor expansion along the second row. Okay, so use the second row here to do cofactor expansion and see what you get. And what you're going to get, I can pause this video and check it for yourself, but then when you resume the video, what you're going to get is exactly what's inside this bracket here, this pair of brackets. So let me add that. I'm just going to add that as a comment. This is cofactor expansion of A along the second row. Okay, and I'm going to put an arrow. I'm talking about this expression in here. Everything inside the brackets. So as a conclusion, what you really have is that this is just the determinant of the original matrix A. So you end up with 4 times the determinant of A, and that's how we get this conclusion over here. Okay, and that is just one, that's just the case of 3 by 3 matrices, and that's only one example of a non-zero constant you can multiply a row by, right? You can multiply any row by a non-zero constant. It doesn't have to be 4, but in general, this same sort of phenomenon will occur, and so it generalizes to the following. So we can write a rule. Well, up here we had a rule to summarize. We're going to have a rule to summarize this as well. So, and I'll write it in the same fashion. So if you can carry the matrix A to some matrix B, specifically by taking a row and multiplying it by a non-zero constant. So I'll say if A can be carried to B by multiplying the ith row by the non-zero constant K, well, then we're going to have the same thing happening. The determinant of B is going to be K times the determinant of A. And really, this is only an elementary row operation if K is a non-zero constant. But if K happened to be 0, this is still technically true, right? Because then that would mean that B had a row of zeros, in which case determinant of B would be 0, which that also comes from this formula, because in that case K would be 0. So I don't actually have to stipulate that K be a non-zero constant in here, but usually that's the context in which you would apply this, right? If you don't, it's not really a row operation unless K is a non-zero constant here, but we don't need to technically write that because it just happens to be true even if K is 0. Okay, and then the last row operation that we haven't discussed yet is you can add a multiple of one row to another. Right? And it turns out as complex as that row operation would seem, I'm not going to prove this to you. I'm just going to state it. It turns out it has no effect on a determinant. If you can add any multiple of any one row to any other row, and you won't change the determinant one bit. So that's something that we can put in for the last rule here. So I'll say if A can be carried to B by taking row I and replacing it with row I plus C row J. That's really the notation you'd use for adding a multiple of one row to another. If A can be carried to B using that operation, then turns out B and A have exactly the same determinants. And that's the third property. So that tells us what effect row operations have on determinants. And the idea is, and we'll see some examples of this soon, if you want to take the determinant of a matrix, you can instead perform row operations first and manipulate it into a friendlier form. And maybe you want to introduce some zeros, because you always like to have zeros when you're choosing a row or column to perform cofactor expansion along. It's just a matter of keeping track of the effect that your row operations are going to have on the determinant, because you can't just perform a bunch of row operations and then not pay attention to the fact that you've changed the matrix, because if you change the matrix in general, you may change the determinant. But by keeping track of which row operations you do along the way, you can keep track of exactly how your row operations have affected the determinant, and then you can still come up with the correct answer.